All right, this is the real opener. I'd like you to write the first three terms in the expansion of x plus y quantity to the 15th power. Go ahead and hit pause and work that out and get back to me in about half an hour. No, I'm just kidding. You probably don't want to try and do that on your own. Well, we did learn that there's a pattern to the coefficients. So first let's write it out. We know that we have x to the 15th and y to the 0. And then we'll have x to the 14th, y to the 1st. And then we'll have x to the 13th, y to the 2nd, etc., etc. This only wants the first three terms, so I'm well on my way. But the question is, what about the coefficients? What goes in these spots? Well, I'm pretty sure that that's going to be a 1, based on what we looked at for Pascal's triangle in part 1. But the problem is, notice we have 1s in all the diagonals here and here. But the problem is, the 5th power, that was the 1st, 2nd, 3rd, 4th, 5th, that was the 6th row. So the 15th power, I need to go to the 16th row. And that's a gigantic triangle, and that seems like that's not the most efficient way to do this. So there must be a better way to handle this. It turns out there are. Binomial coefficients, which we saw in Pascal's triangle, have a pattern to them using combinations. And so to find the coefficients of all these terms, we need to use what we've learned about combinations. N choose 0, n choose 1, n choose 2, n choose r, all the way up to n choose n. And we know n choose n is equal to 1, and n choose 0 is also equal to 1. And so if we can compute whichever coefficients we need using combinations, and we understand the pattern of our variables and their exponents, then we can come up with an expansion for a plus b to any power, or x plus y to any power, any binomial raised to a power, using this idea. So we'll go back to that opener in a second. A shorthand way of writing this theorem is by doing it this way. Now let's rotate this. Rotate it that way. So sigma, summation, we're adding up a bunch of terms. We're going to start with r equals 0 and go all the way until r equals n. And our coefficient is defined as n choose r. So when r is 0, we have n choose 0. Then r bumps up to 1, we have n choose 1, etc., until we get to r equals n, and it'll be n choose n. So that takes care of the coefficients of each of our terms. And then the pattern with our variables, well, we'll start with a to the n minus 0 power, so that's a to the nth power, b to the 0 power, and then as r goes up, the powers of a are decreasing and the powers of b are increasing. So a is going n, n minus 1, n minus 2, all the way down to 0, and b is starting at 0 and going up 1, 2, 3, etc., all the way to n. And so this sigma notation is just a shorthand way of writing the binomial theorem. All right, so let's try and use that and go back and solve that opener. So we already know that first term is 1, but we'll come back to that in a minute. Let me erase these. And let's fill in, this is n choose 0, n choose 1, n choose 2. Now, what is n in this case? N is always the power of our binomial that we're raising this to. So I can fill that in with 15. And let's do some calculating. We know 15 choose 0 is 1, so we're going to get 1, x to the 15th, y to the 0, And then we're going to get plus, what's 15 choose 1? That's 15. You can check that out by following the pattern. Remember, that's 15 factorial, 1 factorial times 15 minus 1 factorial. Well, all of these are going to cancel with everything except the 15, and we're left with just 15 over 1. And then we have x to the 14th, y to the 1st. And what's 15 choose 2? Well, that's 15 factorial over 2 factorial times 13 factorial, which is going to leave us with a 15 and a 14 on top. All the rest cancel with the 13 factorial. I can reduce the 2 and the 14. So I'm left with 15 times 7, which is 105, x to the 13th, y squared. This said just the first 3 terms, so I can stop. And there's my answer. If you want to double check that, you can go ahead and multiply this by itself 15 times. I don't think you want to do that though. So this binomial theorem is really powerful and helps us simplify binomials very quickly. One thing I wanted to point out is sometimes you will see in some books when they list their binomial theorem, they'll start with n choose n, and then n choose n minus 1, all the way down to n choose 0. And because of the symmetry and how 8 choose 5 is the same as 8 choose 3, we know that that's fine, that we'll get the same values there, and also from Pascal's triangle with the symmetry of our numbers as well. I like to do it with n choose 0. It makes more sense with the sigma notation. And so then I always remember that whatever term I'm looking at, if I'm looking at the third term, I know it's the second variable raised to the 3 minus 1, or second power. And then when I'm doing my combination, it's n choose whatever number this second variable is raised to. So that always matches that. These two together should always add up to n. And in our opener that we did, that indeed was the case. 14 plus 1 is 15. That's 15. 13 plus 2 is 15. And notice that the exponent of y always matched the bottom number in our n choose r. 1 matches with 1. 0 matches with 0. Okay, so let's try some problems. And you might want to hit pause, try them, and then compare and see how you did. It's better than just watching me walk through them. All right, expand 2x plus 1 to the 4th. Now, it's not just simply x plus y or a plus b, so we have to be a little careful here. So let's start with, first of all, we know our coefficients. We have 4 choose 0, and then it's going to be the first term, which happens to be 2x to the 4th power, and the second term to the 0 power. Then we're going to do 4 choose 1 for the coefficient. Now it's going to be 2x to the 3rd power, and 1 to the 1st power, etc. 4 choose 2, 2x squared, 1 squared. 4 choose 3, 2x to the 1st, 1 to the 3rd power, and finally 4 choose 4, 2x to the 0 power. Why is he writing that? Just to make sure you're seeing the pattern. Shortly, I'll stop writing all the non-essential stuff. So 4 choose 0 is 1. 2x to the 4th power, well, it's 2 to the 4th power, so that's 16. And then it's also x to the 4th power. Remember, it's 2x times 2x times 2x times 2x. And then 1 to the 0 is 1. 4 choose 1 is 4. 2x to the 3rd power is 8x to the 3rd times 1, plus, now what's 4 choose 2? 4 factorial over 2 factorial times 2 factorial, and that should equal 6, because we'll have 4 times 3 over 2, 12 over 2 is 6, check. So we get 6, and then we have 2x squared, that's 4x squared, 2x times 2x. 4 choose 3, well that's the same as 4 choose 1, so I know that equals 4 times 2x times 1. And then 4 choose 4 is 1, 2x to the 0 is 1, 1 to the 4th is 1. So our final simplified answer is 16x to the fourth plus 32x cubed plus 24x squared plus 8x plus 1. Now notice the coefficients here, 16, 32, 24, 8, and 1. Those don't come from Pascal's triangle, but the numbers 4, choose 0, 1, that was from Pascal's triangle. So it's only this, that's coming from Pascal's triangle. But because we have our term here with a 2, that throws off what our final result is for our coefficients. And that's why there's not a symmetry involved there. Let's try another one. Find the first three terms of x minus 1 to the 7th. Hit pause, give that a try. Okay, here we go. 7, choose 0. And we're going to have, I don't need parentheses on that. We're going to have x to the 7th, negative 1 to the 0. This is the key to getting the correct answer here. Think of this as x plus negative 1. Because that binomial theorem worked for a plus b, or x plus y, plus the first three terms. So the next term is 7, choose 1, x to the 6th, negative 1 to the 1st. And then the third term, 7, choose 2, x to the 5th, negative 1 squared. So our final answer, that's going to, 7 choose 0 is 1, x to the 7th, 7 choose 1 is 7, x to the 6th times negative 1, plus 7 choose 2, 7 times 6, 42 divided by 2 is 21, x to the 5th, negative 1 squared is a positive 1. So we're going to be alternating signs here. It's x to the 7th minus 7x to the 6th plus 21x to the 5th. First three terms, I can stop, and I'm done. How do we do? All right, let's look at another example. Find the term containing x to the 6th power. All right, there's two approaches here. There's the force my way through and let's just work this whole thing out. 9 choose 0, blah, 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 x to the 9th, 3 to the 0, and I'm tired already. And then just figure out which one has x to the 6th. Or I can think about which one's going to have x to the 6th. If I have x to the 6th power, then it's going to be times the other term. We have x, we have 3. The other term will have to be to the 3rd power because they should add up to 9. And then my coefficient is going to be 9 choose 3 because, get an arrow here. Remember, this matched the power of the 2nd term. And so that's all I need. I don't need all the other terms. So I work that out and I figure out what's 9 choose 3. And I can grab the calculator, or I can do it by hand. Let's do it by hand. 9 factorial, 3 factorial, 6 factorial. That's going to be 9 times 8 times 7. The rest cancel with the 6 factorial. 3 times 2. 12 times 7 is 84. So we get 84 x to the 6th times 27. And then I have to multiply 27 times 84. Okay, I give up. I'll use the calculator. 2268. So final answer. (2,268 x to the 6th). It said, and reread the directions, find the term containing x to the 6th. And that's it. All right, let's try one more. Find the coefficient of the term containing x to the 5th in the expansion of. All right, this is slightly more complicated. Let's break this down. First, we need to focus on this. I'm going to multiply all that out using the binomial theorem. Then after I do that, I'm going to multiply the answer times x plus 3. So think about what that's going to look like. You can do a lot of work and just work out the whole thing, and then find the coefficient of x to the fifth. Or, all right, I'm going to have 6 choose 0, 2x to the sixth power, negative 1 to the 0 power. And then I'm going to have 6 choose 1, 2x to the fifth, negative 1 to the first. Then I'm going to have 6 choose 2, 2x to the fourth, negative 1 squared. Then I'm going to have a bunch of other stuff. Why did I stop there? I stopped there because after I get that, this is the term that's going to have an x to the fifth power. Not this one, not this one, not any other one. That'll have x to the fifth. But then I have to multiply this binomial times all of those terms. Now, when I multiply x times this first term, this is an x to the sixth, so x times that will give me an x to the seventh. I don't need that. That's not x to the fifth. When I multiply the x times the second term, which will have an x to the fifth, that'll make it an x to the sixth power. Not interesting. Finally, though, when I multiply x times this third term, which has an x to the fourth, I will get an x to the fifth. So that's one that I'm interested in. So I want to multiply this x times this term here. That's going to give me an x to the fifth. But I also know when I multiply the 3 times everything, 3 times this term will wind up being an x to the sixth power. But 3 times this term is another x to the fifth power. So I'm interested in that one as well. So 3 times this term will also give me an x to the fifth. So here we go. Let's take the x times 6 choose 2. And put parentheses. What is 6 choose 2? 6 factorial, 2 factorial, 4 factorial. That's 6 times 5 over 2. That's 15. 2x to the fourth. 2 to the fourth is 16. X to the fourth. Negative 1 squared is a positive 1. All right, so that's the green. I should have done that in green. That's the green. Okay, now let's do the purple. And that's going to be 3 times 6 choose 1 is 6. 2 to the fifth is 32. X to the fifth times negative 1. So I'm going to wind up with 15 times 16, which is what, 240? X to the fifth plus 3 times 6 times 32. That's a lot. Maybe I should use a calculator. Or 180, well, let's use a calculator. 18 times 32. 40, 500 something. 18 times 32. 576. So we get negative 576 x to the fifth. Okay, now I can combine like terms, and I get my final answer, which is going to be a negative 336 x to the fifth power. Pretty happy with myself. Think I did everything okay. I should double check, make sure I didn't make any arithmetic mistakes. But what I always want to make sure that I do when I finish a problem that requires a lot of computation and small pieces is reread the directions. And my directions say, find the coefficient of the term containing x to the fifth. So the correct answer to this would be negative 336. I don't want to include x to the fifth in my answer. All right, so there's some examples of how to use the binomial theorem and how to make your life a lot easier. You can still do things the hard way and multiply everything out, but it'll take you a lot longer. And here's the problem set, 8.4, starts on page 604.